those of you who don't know what proprietary trading is, it's a special kind of structure to the exchanges, usually a member structure, which has very high costs, high barriers to entry. Lots of different strategies have capacity constraints. We typically get very low fees and potentially can use very high leverage. But one of the really key points here is I'm not here to sell you anything. We don't have customers. We're not allowed by law to have customers. All the money that we invest is either the firm's money or the partners of the firm's money. So I've got nothing to sell you, but I do have a story to tell you. There we go. So, what is machine learning really? You're hearing a lot about it now, along with big data. But machine learning came out of the artificial intelligence research that started in the 50s and 60s, and originally was aimed at creating human-like intelligence. That didn't work out so well. There's still a very tiny corner of computer scientists who are working on human-like intelligence. But for the most part, they rebranded it as machine learning and took a set of models that are about drawing inferences from data, usually in a non-parametric way. There are a whole bunch of references at the end of the slides. I'm sure that the organizers here will post the slides later. But there's a couple of books that are pretty good at this. Bradley Efron and Trevor Hasty wrote Computer Age Statistical Inference. Bradley Efron was the creator of the modern bootstrap. And Domingos's master algorithm is a popular text. There's no math anywhere in it, but it's aimed at understanding machine learning by somebody who's actually been doing this for 30 years. So we're going to talk a little bit. I'm not going to talk about specific machine learning models except in passing, because fundamentally they all do very similar things. And if you have enough data, you can probably get almost any algorithm to give you an answer from that data. So what I'm going to talk about instead is I'm going to talk about some of the features that these machine learning models have and how you might then apply them to a set of use cases in trading. So is it all about the data? We're moving, as Stuart mentioned up here in the last panel, we're moving from somewhere around 100 gigabytes a day of market data capture across global markets to over 1 terabyte a day of market data capture as the exchanges put more and more data into what they're doing. Many vendors, including Reuters, IBM, Bloomberg, are selling new data sets. Some of the biggest users of machine learning in trading, the Renaissances and Two Sigmas and Citadels of the world, are spending tens of millions of dollars a year creating unusual or unique data sets, or data sets that almost no one else has access to. So there's a ton of data things here. So in many cases, you might have tens to hundreds of additional descriptive data sources available when you build your models. But we have a problem. If we just throw all the data into a pile and mix it all up, we don't tend to get a very good answer. I don't care how sophisticated the machine learning model is that you throw at it, you're not likely to get a good answer out of just mixing it all up in a pile. So what about the features? I think feature engineering is one of the things that I hope you take away from this. The firms that are doing this for real are spending tons of money engineering features that in and of themselves have some predictive value. So, fundamentally, the data isn't the main thing anymore. When we started building time series models, 25 years ago and 30 years ago, when people were doing time series models, they typically were using the market data primarily. Today, when you're building time series models, of course, you still need the market data, but that's not going to be the primary driver. The primary driver is taking the primary market data, taking extra data that's related to your market data, and building features that have some predictive value. So it's often better to engage in feature engineering than it is to just think about what model can we apply or what are we going to do otherwise. So that's transformations of the data, that's putting the data into categorical or integer states or factor data, that's adding features that are indicative of your objective. So if there's something that you want to accomplish, you can ask, how can I build a data set that goes along with my data that would tell me about what might happen in the future? So when I'm looking backwards, I can say that I had certain features there that could tell me what might have happened coming up. Although what I just said is also very dangerous. There's a specific type of bias called look-ahead bias that can convince you that you're brilliant and then shoot you in the foot. So be careful about that kind of feature. and using extra models for things like seasonality or collinearity. So one of the things that we find, and I think other people who do this stuff find, is that you end up combining multiple models where you put specific models together that are good at one or more things, that you are part of what your objective really is. So now let's talk about the models. And we're going to talk really about features of the models for the most part, but I'm going to start with rules engines. Some of the very first artificial intelligence models were what are known as expert systems. And they were effectively a set of rules that were created by a series of experts that described some known system. And this was originally, the idea was that if we wanted to learn about medicine, we would get a bunch of doctors together and create a bunch of rules for doing things, and that then we would create a medical expert system that would be able to tell us about how to diagnose a patient. It turns out these systems didn't actually work very well. They were very popular in the 1980s, but notably, if you think about that, computers in the 1980s were really, really slow. So you had to use these kind of expert rules and do this kind of if this, then that kind of decision making to get anywhere in the 1980s. But you really didn't get good answers out of most of these systems. So they mostly fell to the wayside as computers got faster, which is one of the key things that you need to understand about the ascendancy of machine learning now. These models are almost all simulation-based. They do thousands or tens of thousands or hundreds of thousands or millions of simulations to get to an answer that's probabilistic in nature. So the rules expert systems kind of fell out of favor as computers got faster, but you need to think again about what I said a little earlier. The people who are actually doing machine learning are spending millions of dollars a year, in some cases tens of millions of dollars a year, engineering features to put into their models. So even though the old rules-based expert systems are largely gone, feature engineering is one of the most critical things that we do today in computer trading or machine learning-driven trading. So now I'm going to talk about optimization as a feature. Optimization, of course, is an end unto itself. We'll talk about it again when we get to use cases. But almost all machine learning models, if you pull apart the model itself, you look inside the black box and you say, what's it doing? Almost all of them have an optimizer in them. Because what they're doing is they're taking all this data that they created, these tens of thousands of simulations or hundreds of thousands of simulations, and they're optimizing it to find a local minima or maxima. That's an optimization problem. So I think it's really important if you're going to think about going into machine learning or looking at machine learning and how you could apply it in your business, you really need to understand optimization first. In the references, there are two lectures at the Simmons Institute, who of course is the head of Renaissance, by Ben Recht, who talks mostly about convex and closed form optimization, but it's really important to understand those basics to get at what we're going at. But also, when you get into machine learning, you're talking about what I call stochastic models, the global stochastic models. Remember, one of the key things that's going on here is that we're doing a bunch of simulation. That means that we have randomized simulation that we are then going to work on finding an optima out of. There we go. Whoops. Backpropagation is a specific model type that you hear mostly in terms of neural networks. But fundamentally, what backpropagation is about is that it's looking at something I already know and a set of connections that I've already identified. And as I learn more about the model, I go back into the old parts of the model and I either reinforce or underweight the connections that I built. So what we're doing with backpropagation is really putting a stronger path. You're wearing a path in the model. As you get more and more reinforcement of the model, you're wearing a stronger path through it so that you're more likely to follow that same path in the future. It's closely related to gradient descent and policy gradients. The most famous models employing backpropagation, as I said already, are neural networks. Deep learning, you'll hear about a lot. Deep learning is really mostly, I mean, there are other ways of implementing it, but fundamentally, almost all deep learning models are neural network models that have more layers. In the 80s and early 90s, when we were doing neural network models, we only had 2, 3, 5 layers in the neural network model because computers just weren't fast enough to do more than that. Many deep learning models may have hundreds of layers, and therefore, thousands and thousands of nodes that they are creating connections between. So this is really one of the oldest truly learning approaches. So, if you think about it, it's really about learning from the data that comes in over time to build a pathway that you can follow. Evolution is another key feature here, that what we want to do as we learn is we want to mix it up a little bit. I'm using the evolution. There are technical terms called crossover and mutation here. Crossover is taking successful features from your population simulations and mixing up your successful features. Mutation is mutating, both successful and unsuccessful features to try to find a combination of things over time that is more successful. So certainly you see this in optimization models, but you see it extensively in other machine learning models as well. Probabilistic inference. I've talked about how a lot of this is building large models that then come up with a probability that one thing or another is true. So the feature that we're talking about here is really building up those probabilities such that I can make a better decision. It's inherently computationally intensive. Bayesian models are all probabilistic inference models. So every Monte Carlo model is a probabilistic inference model. Every Bayesian model is a probabilistic inference model. Many genetic algorithms are probabilistic inference models. But these are very, very computationally intense. Similarity is an area of machine learning that doesn't get a whole lot of coverage, but it's largely used in kind of regression and classification models. But k-means clusters, support vector machines, kernel models are all similarity models. So this kind of clustering or classification task is a task that you'll see used over and over again. We skipped a slide on gradient descent because I don't know how to use the clicker. But gradient descent is really what it sounds. It's about walking down a hill until you get to the local minima, and then walking down that hill further until you get to the furthest down you can get. And it's used heavily in optimization and some of these other transformation models. So one of the things about machine learning is that it's very easy to get it wrong. Overfitting is a huge problem in machine learning models. And so you need to think about the ways that you can figure out if you've gotten it wrong. As I said, I'm in prop trading, so the money that we invest is my money and the firm's money. I really don't like getting it wrong because it's taking money out of my pocket directly and giving it to the market. But it's very, very easy to build a trading strategy that you think is brilliant because it works in all of your tests and it looks like it's going to be awesome, and then it doesn't make money at all. So I'm not going to go through all of these. They're really there for you to look at later and reference later. There's references on all these. But there's a whole bunch of tests that you have to be familiar with and you have to actually use to try to convince yourself that you're incorrect. One of the things that I say in a lot of the talks that I give is that this is a scientific process fundamentally. And the scientific method is about proving your hypothesis incorrect. Not demonstrating that it's correct, but proving that it's incorrect. So you have to start with the assumption that any model that you're creating is wrong. There's also a bunch of specific models for detecting backtest overfitting. And again, these are really references for you for later. I'm sure that the slides will be available. And if they're not available, send me an email and I'll send them to you. But these are also incredibly important to look at. Now, what you all really wanted to hear about was the use cases for machine learning and trading. Robert Gentleman is one of the creators of the R programming language. He says that a big computer, a complex algorithm, and a long time does not equal science. Throwing a ton of data at the model and asking the model to tell me whether markets are going to go up or down in the next minute, hour, day isn't actually a good way to do this. So how are people actually using machine learning models? And let's walk through them kind of in increasing complexity, let's say, and probably decreasing likelihood that anybody's actually doing these things. So the most common usage of machine learning in trading is as regression models. That sounds really kind of crazy, but most of the time what you're doing is you're trying to predict a value like the mean or the median. You're trying to predict the slope. You're trying to predict direction. That's a regression model. That's nothing different than a simple linear regression would give you, except of course linear regressions aren't very good at it because most of the data that we deal with is fat-tailed, it's non-linear, it's non-stationary. So you're still trying to get a regression model out of this, and most of the people who are using machine learning and trading are using it for regression. You can do this directly with a model like logistic regression. Logistic regression is a funny model because logistic regression was invented in the 1850s, but it's still considered a machine learning model because of the way that it actually comes to an answer, that it learns from the data to come to an answer. But it's a model that's been around for 150 years. Bayesian regression, now we're getting into things that sound more like machine learning. As soon as you throw the word Bayesian in there, it's obviously a machine learning model. It's one of the classes of models that Domingos talks about in his book, The Master Algorithm. Random forests. Random forests, it sounds really cool. It's a great name. Random forests are regression trees. That's all they are. It's just thousands of regressions compared against each other to figure out what the probability that one answer is more likely than the other. So it's just thousands and thousands of regressions done over and over again. Boosting is another way of taking a set of regressions and using them to simplify the model. Or indirectly, Monte Carlo models, gradient descent models, state space models, optimization models with the correct objectives. But in many cases, what you need to be aware of, because all you're doing is a regression, a simpler model might work a lot better. I know of one very large proprietary firm that was later bought by a fund and then later bought by a bank that started out using wavelet models and neural networks and ended up using ridge regression as their main predictive tool. So you need to think about, at any point, again, I hope this is a key takeaway, what's the simplest possible model that you think might be directive towards what you're trying to solve? And start there. Start with the simplest possible model that you think might work, and then go to a more sophisticated model. Because these types of models, if you work on them, you can spend weeks or months fitting one of these models. Or you could spend an afternoon fitting a ridge regression and seeing if you are in the right direction. So start with the simple things and move on from there. So what's next? Optimization. Domingos actually includes optimization as one of his classes of machine learning models. Certainly he's talking mostly about the more sophisticated optimization models, but as I said, gradient descent, mutation, crossover are all features of machine learning models. So you need to consider whether, first, again, whether a simpler model is going to work, because there's a lot less model risk. Model risk is a term I haven't introduced yet, but it's really critical. As the model itself gets more complex, the likelihood that you're going to fool yourself and make mistakes also goes up. So to avoid model risk, you should try to use the model with the least parameters, the model with the least complexity, the model with the least features that you can to get an answer, and only later work towards more complex models. Optimizer parameters for the optimizers can have a huge, literally orders of magnitude, 1, 2, 3 orders of magnitude difference in how fast and how well the optimization algorithm will converge. And this is actually true across most machine learning models. So you need to be very careful that you understand the models that you're using. These really aren't black boxes. I've read a lot of papers written by academics, and we've replicated a lot of these papers, and we typically find these models that the academic models are massively overfit, that they've done a very careful job of selecting their data, that they've run through their feature selection, they've thrown things out, and when you try to apply it to real data, it often doesn't work. So typically, you need to be very careful about, these aren't black box models. It's not press the button and go and out comes a trading strategy. We'll talk more about that in a little bit. But many other problems can be recast as optimization problems. So process control or optimal process control models, capital allocation models, risk allocation models or risk management models, adaptive parameters. Like one of the things that you often do with trading strategies is you try to figure out which knobs and levers you need to pull at a given time to make the trading strategy work. That's just parameter optimization. Again, it's an optimization problem. The next class of models I'll talk about is classification or clustering. Many machine learning models are purely classification models or clustering models. But again, you could try a very simple clustering model first. You could try a k-means cluster first and only then go to a support vector machine. Because a support vector machine can be misfit very easily, whereas a k-means cluster either says I've got clusters or I don't. And so if the k-means cluster says I've got some clusters and they make sense to you, they make logical sense to you when you look at them, then you can think about going back and applying a more complex model to the problem. Oh, one of the other things I'll say about classification models is usually the classification model itself isn't the end goal. Usually the classification model is creating a classification, it's creating a label for your data such that some other model can make a decision. Like I may have a model that does really well in uptrending markets and a different model that does really well in downtrending markets, or a model that does really well in a high volatility situation versus a low volatility situation. So a classification model is really about giving me those states so that I can then apply some other model to actually do the trading. Composite models, now we're talking about what people are often speaking about when they talk about machine learning and trading. The head of WorldQuant, Tolchinsky, calls it lots of little models. He calls it lots of little alphas. They publish papers on how do you combine thousands of alphas. In this case, what you're fundamentally doing is you're taking hundreds, thousands, in some cases even 1 million features. We talked about feature engineering earlier. And then you're using the machine learning model to make these weak learners, these things that are only weakly predictive in and of themselves, into a stronger learner, into a stronger model in and of its, to a stronger model once it's together. Now, one of the problems that should be immediately obvious from what I just said is that I talked about hundreds, thousands, even 1 million features. Where do you get those hundreds, thousands, even 1 million features? Well, you've got to spend a lot of time and money to build those things. So the big firms, WorldQuant, 2 Sigma, Kepos, Jump, Bridgewater, Citadel, are all doing this. But they have the money and the resources. They have the armies of analysts. They have the data to do it. So if you're in the audience and you're from one of those places, you already know this. I'm not telling you anything you don't know. If, however, you've been thinking about applying machine learning models and you want to go down this path, and what you're thinking you're going to do is get a bunch of data together and spit out a trading strategy, that's not going to happen. The head of Kepos Capital told me several years ago that his model contains a few hundred features, each of which in and of itself is a profitable trading strategy. So each of the features that he feeds into his primary model he could run it on its own and it has a positive expectation. Mixing them up together makes it a better expectation, by using the machine learning model on top of things to make it better. But you had to first have 100 strategies. That's hard, especially if you're small. Now, the Holy Grail, model discovery. Can I use machine learning to discover a model to trade? Like the Holy Grail, it's probably a myth, or mostly a myth. Feature engineering is really what makes these models work. So you need to think about what features, what inputs can you create that have some value in and of themselves. Then using a machine learning model to combine those features, select among those features, and get some value out of those features is very feasible. Machine learning doesn't create a model on its own. Many good features and data sets are what really make model discovery possible. It doesn't happen all on its own. So what you need to focus on is curating your data, keeping good data, keeping clean data. Any quant will tell you that they probably spend 75% of their time munging data. That really what you spend all this time doing is getting the data into a form that you can analyze it, and keeping it in a form that you can analyze it tomorrow and the next day and the next day. And then after you've done all that, turning it into a form that you can feed it into a trading system. So doing that kind of data curation and feature engineering is really where most of the effort is and where most of the time is spent. With enough data, models, and features, you have a broad choice of algorithms. One of the things that you should be very aware of is if you have enough features, you could use any of the models that you hear about. You could use a random forest, you could use a neural network, you could use a deep learning model, you can use an optimization model, you can use a classification model. All of these things are likely to be able to give you the answer you want if you have the features to feed into it. If you don't, as the number of data and features that you have available to you decreases, the models that you can employ with that data and features actually goes down. As I have less and less data, the likelihood that I can build a successful model decreases. It becomes harder and harder to do. But as I have more features, I have a larger choice of models that I can use to solve my problems.